Hackers and hackerettes, welcome to our very first video in the software basics playlist or path or whatever you want to call it of the TryHackMe pre-security. And here we're going to be talking about the data representation. So this is the first video in this playlist, but we have been going through the TryHackMe pre-security path, and we have finished all of these modules on video. So I do have a playlist called pre-security, so watch that if you want to watch all of the pre-security videos in sequence. Well, let's get started. The introduction. Are you curious to explore the in-depth how computers represent colors and numbers? You are not only interested in seeing purple color on the screen, but also interested in inspecting how this purple is represented in the computer memory. As a bonus, you'll also learn how computers manage to do all their calculations when they can read and write only two states and interpret them as 0 and 1. Okay? Human beings find it most convenient to use the decimal system for everyday tasks, such as counting, measuring, weighing, and paying. If you like jogging, you might track your progress by timing yourself. For instance, you might say you jogged for 23 minutes. When you look at prices, you expect something like $17.99 to $39, $3,049, and so on. Without giving it much thought, we use the decimal system, where the digits range from 0 to 9. Computers, on the other hand, are limited to two digits, 0 and 1. If you have ever wondered how computers represent the different values using only two digits, this room will help you get some answers. This is very important for us hackers, because if we do not understand this basic concept of a bit and how binary works like 1 and 0, we will be not having an understanding of the most basic thing in computers and how information is represented at the lowest level whatsoever. So it is very important to pay attention here. This is also like a new topic for me. I know what binary is. I understand that 1 is essentially the on state and 0 is the off state. So 1 means yes electricity and 0 means zero electricity. And then you check for electricity, no electricity, electricity, no electricity, like millions of times per second. So this is how we can represent like a lot of numbers, but I don't know much about it. So I'll be learning alongside you and trying to explain things as we go through. Let's talk about representing colors. Our first 8 colors. By combining different amounts of red, green, and blue, which is RGB lights, you can get any color you like. In computer colors, think of it like 3 knobs, and each knob controls one of 3 colors. Let's say that each of the 3 colors can be either on or off, i.e. each has 2 states. The red light can be either on or off, green on and off, blue on and off. These states give us 2 by 2 by 2 equals 8. That's 8 different colors. Okay? How does that work? Is because, for example, you could have red on and both of these off. So that's red color. You can have green on and both off. That's green. Blue. That's blue. And then you could have red on and green on with blue off. So that's a fourth color. And then you can have red on and blue on, but green off, and so on. So you get to see how that works, okay? So yeah, you can see here, like for example, red and green give you yellow, red, green, and blue all together give you white. Red and blue give you purple, blue and green give you whatever this is, cyan maybe it's called. I'm not very good with colors. And then you have the RGB themselves. So if a computer were limited to 8 colors, it would only need to indicate which color is switched on and which is switched off. In fact, it can use the 3 digits instead of 1 and 0 to represent the states of red, green, and blue. For example, 111 would be all 3 lights switched on, while 100 or 100 is only red and then both of them are switched off, which would equal the color red. Only the red switched on. The digit or this digit, which can be either 1 or 0, is called a bit. Now a computer can represent any of the 8 colors. If this is still unclear, a detailed list is shown below. So 000 is black, 001 is only blue is on, so red, green, and blue, RGB, and then each state represents that. So R is off, G is on, B is off, so this is green. This is red. This is, yes, it is called cyan, I was correct. But instead of purple, it's called magenta, which is okay. And then you see how this is working. So each color here, or each bit represents a specific color in the RGB values, and then you combine them in order to get 8 different colors. We just provided a way to represent a color in a palette of 8 colors, from 8 to 16 million. Being limited to 8 colors is inconvenient, as we prefer millions of colors. It would be convenient if each of the 3 digits, red, green, and blue, had 256 levels instead of just 2. On or off. Let's repeat the same math earlier. 256 by 256 equals 16,777,216. That's more than 16 million colors. That covers most of our needs. Yeah. I don't know why we have so many colors in the world, but there is way too many colors, and for me, a bit overwhelming. Especially if you're married, you'll probably understand what I'm hinting at. But anyway, 1 bit is enough to represent 2 states, on and off. We need 8 bits to express 256 states. In most textbooks, a group of 8 bits is referred to as a byte. However, you can also use the term octet. Okay? So octet means like eighth, or like composed of 8 things. Okay? Putting all this together, you would realize that a color is now represented as a 3 by 8 bits, or 3 bytes, 24 bits. For example, 1 green color used on this page is represented as all of that. That's not a very convenient way to type or read color codes. Here comes the hexadecimal representation to the rescue. If you have ever worked with Photoshop, or you ever worked with like any colors, even HTML or CSS, you would know that you can set the color using a hashtag, and then like 6 Fs for white or 6 zeros for black, and then whatever is in between. So now this is what is called the hexadecimal representation. Hexadecimal representation makes it easy to combine 4 bits into a single character, a hexadecimal digit. To be specific, for now, please think of the hexadecimal digits as symbols, where each symbol represents a set of 4 bits. We will revisit hexadecimal numbers in task 3. Okay. So hexadecimal digit is 0, binary representation, 4 zeros, 1 is zeros and ones, 2 is 0010, 3 is 0011, 4 is 0100, and so on. And then you have A, B, C, D, E, and F. Going back to green color, instead of typing whatever this is, we can type A3 EA2A. In fact, that's how we specify the color in graphics programs. For your convenience, the attached static site helps you convert a hex color into its binary and decimal representations, along with a color preview. To summarize what we covered so far, in real-life applications, a color is represented in 24 bits, i.e. 3 bytes. Each byte can represent 256 different values. Each of the 3 bytes specifies the intensity of the red, green, and blue lights. Every 4 bits are represented by 1 hexadecimal digit. Each byte is represented as 2 hexadecimal digits. Click on the view site below to answer the following questions. Okay, so let's copy this, submit, and then you get this. Preview the color. What does the color appear to be? It looks green to me. What is the binary representation of this color? Binary is this. Decimal representation of this guy. And here's the decimal. Oh, sorry, that's hexadecimal. My bad. The decimal representation is this. Okay, so we finished actually this, so we could minimize this. And we're going to get to task 2. Numbers from decimal to hexadecimal. Human beings have 10 fingers, and this is the most plausible explanation for why we use the decimal or base 10 system in our everyday lives. Computers, on the other hand, have 2 finger states that they understand, low and high in voltage range. Example, transistor logic. North and south in magnetic polarity, example, hard disk drives. Light presence, fiber optics. So let's consider the first example. On the electronic level, a transistor either passes or blocks electric current. This is what I told you, like 0 being no electricity and 1 being electricity passing. Consequently, in all digital systems, everything boils down to a low or high state, representing 0 and 1 respectively. For example, the low range can be voltage between 0 and 0.8 volts, while the high range is between 2 and 3.3 volts, or 2.7 and 5 volts, depending on the electronic system. We are not affected by how the 0 and the 1 are represented on the physical level. However, we are concerned with how to use these 2 digits to represent data, such as numbers. Yeah, so we don't care about electricity. That's the job of the transistor. But we are caring about, like, whenever we want to represent data using 1 and 0, what can we do? In the previous task, we saw that we can use a set of bits to fine-tune the steps. For instance, 1 bit can represent 2 states, while 8 bits can represent 256 states. In this task, we will learn a bit more about the math behind it. However, don't worry if it appears complex at first glance. Things will make more sense as you progress in your learning journey, and because I'm here, of course. In simple math terms, a number such as 213, 213, is actually the same as saying 200 plus 10 plus 3. Isn't that right? Yeah. In a more technical representation, 213 can be written as 2 times 10 to the power of 2 plus 1 times 10 to the power of 1 plus 3 times 10 to the power of 0. Now, 10 to the power of 0, it actually resolves to 1. So this is why this is equal to 2 times 100, which is 200. 1 times 10 to the power of 1, which is 10. So this is 200 plus 10, and then 3 times 1 is 1. 200 plus 10 plus 1 is 213. Okay? So if you didn't know why, anything to the power of 0 is 1. As you would remember for the math class, 10 to the power of 2 equals 100. 10 to the power of 1 is 10, and 10 to the power of 0 equals 1. Okay? Consequently, this was just the formal mathematical way of saying 213. If you have not worked with math for some time, please give this some thought and a second read before you move on. So yeah, essentially, it is really simple once you, or if you know basic math. And if you don't know what to the power means, so if you don't know what this means this number multiplied by itself. Multiply by itself the amount of times that it is to the power of. For example, let's open up calculator so I can explain this. So 10 to the power of 2 means 10 multiplied by 10, which gives me 100. Now I want you to imagine 10 to the power of 3. So that's 10 multiplied by 10 multiplied by 10, which is 1000. So 10 to the power of 3 means 1000. Okay? Next, 10 to the power of 1, anything to the power of 1 is just itself. So 10 to the power of 1 is 10. Because to the power of 1 means this number is just sitting alone. It's not doing anything. And then 3 to the power of 0, anything to the power of 0 is 1. So I'm going to say here 10. And then to the power, oh, that's the, why is this the square root? I want to the power. So if I write 10 to the power, how can I write to the power, sir? I actually don't know how to write to the power in this calculator. Programmer, can I have to the power in programmer? Bitwise and bit shift? No, I don't want that. I mean, x to the power of 2. Why doesn't it say square root? Cannot divide by 0. Yeah. This looks like to the power to me. I don't know why it's whatever this is. So 10 to 10 to the power of 3 is 1000. So you can just write it in Google here, because I don't know if I'm stupid, can I use calculator, or because calculator is stupid. But anyway, let's say 10 to the power of 0, which is what we were working on. And this is going to equal to 1. Okay? Now let's go to binary numbers. The binary base 2 system can be expressed similarly to what we wrote earlier, discussing the decimal base 10 system. Okay? The key differences are that the binary system is limited to 2 digits, and everything is a power of 2. Let's consider a couple of examples. The binary 1001 can be represented as follows. 1 multiplied by 2 to the power of 3. 0 multiplied by 2 to the power of 2. When 0 is divided, or when multiplied by anything, is going to go 0. Okay? So whatever this is going to be 0 at the end. This is also going to be 0. And then 1 to the power of 2, or sorry, 1 multiplied by 2 to the power of 0. This is also going to result in 1. So the total result of this is 1. Okay? So 1 multiplied by 8 plus 0 gives me 8. Or sorry, 1 multiplied by 8 gives me 8. 0 multiplied by 4 is 0. 0 multiplied by 2 is 0. And then 1 multiplied by 1 is 1. So 8, 0, 0 plus 1 equals 9. We just demonstrated how to write 9 in binary. So this 1001 is 9. Okay? Now, the way this works is, this might be a bit confusing for you, but we can get a bunch of things to understand. So let's say that everything is to the power or like is a power of 2. So it's going to be multiplied by 2, and then we're going to decrease from to the power of 3 to the power of 2 to the power of 1 and to the power of 0 at the end. Okay? So you can see here that in every equation we are doing the exact same thing. We're getting the number that's right here, and then we're multiplying it by 2 to the power of, and then 3, 2, 1, 0. So as an example, let's take a separate example here. I'm gonna say 1, 1, 0, 0, I guess. So let's start. This is gonna look like this. 1 multiplied by 2 to the power of 3 plus 1 multiplied by 2 to the power of 2 plus 0 multiplied by 2 to the power of 1 plus 0 multiplied by 2 to the power of 0, which is going to give me 0, 0. Okay? Then we can calculate this. 2 to the power of 2, if you don't know how that is, that means 2 multiplied by 2, which is going to give me 4. Okay? And then 2 to the power of 3 is 8, because 2 multiplied by 2 multiplied by 2, 2 multiplied by 2 is 4, 4 multiplied by 2 is 8. So this is going to be 8 plus 4 is going to give me 12. Okay? So 1100 in binary or in hexadecimal is going to give me, or sorry, in decimal, binary to decimal converter. So here, enter the binary number 1100. We are going to get 12, which is 8 plus 4. And you can see here how it works. 1 multiplied by 2 to the power of 3. 1 multiplied by 2 to the power of 2. 0 multiplied by 2 to the power of 1. And 0 multiplied by 2 to the power of 0. which is going to give me 12 at the end to the base 10. So we are using 1100 base of 2 to 12 base of 10. Now, if you still do not understand this, I'll just go over one more example real quick, and we're going to move on because I think this is going to be like really important and really cool for you. I'm going to add 1110, which is going to be like a big number. Okay, so let's see how much we can get here. So it's going to be 1 multiplied by 2 to the power of 3, 1 multiplied by 2 to the power of 2, 1 multiplied by 2 to the power of 1, and then 0. We're just not going to type it because 0 multiplied by 2 to the power of 0, which is 2 to the power of 0 is 1. 0 multiplied by 1 is still 0. So I don't care about this one. So let's see here. 2 to the power of 1 is 2. 1 multiplied by 2 is 2. Now here 4. And here is going to be 8. So 8 plus 2 is 10, and then 4 is 14. So 1110 should equal 14. Let's see if I'm correct. And there we go. Okay. So this is how you can do it. The idea is whatever number is written here, you then multiply it by 2 to the power of whatever position it is in right now, starting from 0, of course. So on the far left, it is the highest number. So it is to the power of 3. Here it is the second to the power of 2. Here multiply by 2 to the power of 1. And here multiply by 2 to the power of 0. Okay? So this means that whatever digit is here, it's actually going to be the digit itself. So it's either 0 or 1. This is why, by the way, that this is 2 in binary. Because if you think about it, 0, so everything that is 0 is going to be 0. So 0, 0. This is to the power of 3, to the power of 2, and then to the power of 1. So 1 multiplied by 2 to the power of 1 is 2, and then 0. So this is all going to result to 2. This is how we can write 2 in binary. Okay? Now, let's go and let's do 0, 0, 0, 0. Of course, this is going to be 0 because you're just multiplying zeros all together. This is going to give you 0. Now, what is the highest number we can get to? Let's actually calculate it as the last thing. 2 to the power of 3, which is going to equal 8. 8, not 9. 1. 2 to the power of 2. This is going to give me 4. 1. 2 to the power of 1. This is going to give me 2. And then 1. 2 to the power of 0, which is going to give me 1. Now, let's see what is the maximum thing that we can get. 8 and 2 is 10. And then 1 is 11 and 4 is 15. So 1, 1, 1, 1 is going to give me 15. Okay? I hope all of these examples make sense to you because they do to me. Now we can skip these ones. If this is your first time working with different bases, you might have already figured out that the rightmost digit is multiplied by 2 to the power of 0 in the case of the binary base 2 system, and the multiply by 10 to the power of 0 in case of decimal base 10 system. Then the next digit is multiplied by 2 to the power of 1 in the base 2 system, and by 10 to the power of 1 in the base 10 system, and so forth, till we reach the leftmost digit. It is easy, but requires careful attention not to miss any digit or misjudge its power. As an exercise, we will convert 4 more binary numbers to the decimal system. Try to do this on a piece of paper before comparing your answers. I think we already came up with a bunch of these. So we can skip these. Having come this far, it is time to revisit the hexadecimal system. Hexadecimal number. In task 2, we grouped every 4 bits into a single hexadecimal digit, as we've seen earlier. A hexadecimal digit ranges between 0 and F. By taking a closer look at the table below, you will notice that a hexadecimal digit ranges between 0 and 15 in the decimal system. To replace 10, 11, 12, 13, 14, and 15, each with a single letter digit, A, B, C, D, E, and F are chosen. The table below is something you would encounter in any tutorial or chapter on the hexadecimal system. So that means that we cannot have 10, 11, 12, 13, 14, and 15 because our numbers only range from 0 to 9. So these numbers, they will be represented as A, B, C, D, E, and F. F being 15, A being 10, okay? So you can see here what they are equal to. So converting from hexadecimal to decimal. So 9B and DF, okay? Let's think about that. So this, even though this is optional, we're still gonna do it because we wanna understand everything. This subsection is optional. If you are curious about converting a hexadecimal number to a decimal number, you would follow the same approach we used for binary conversion. Let's say that we want to convert the hexadecimal number 9BDF to decimal, okay? Now, if you want to know, you start by A being 10, B being 11, C being 12, D being 13, E being 14, and F being 15, okay? We can use these as this table as a reference. What I'm going to do is I can copy this just to make it easier for you. We can paste it right here. Can remove this. So what we worry about is that we don't care about these numbers here. Or actually we do, never mind. This is the number that it represents. So 15 is being represented by F, and in its binary format, it's 1111. Okay. Let's say we want to convert the hexadecimal number 9BDF to decimal. Let's see how they do it. So 9BDF, so 9 multiplied by 16 to the power of 3 plus 11 times 16 to the power of 2 plus 13 multiplied by 16 to the power of 1, and then plus 15 multiplied by 16 to the power of 0. And you can see that this is 39,903. Why is it 16? Because we're talking about hexadecimal to decimal. All right. So this representation, because this hexadecimal representation only goes up to 16, including 0, goes up to 15, including 0, that's 16 numbers. This is why we're multiplying by 16 here. If you don't understand it, starting from 0 and then going all the way to 15, which is the maximum binary we can represent in 4 bits, 1111, that's 15. But you have to include 0, so overall, these are all 16 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Because there's a 0 in there, you might think it's 15, but all of these are 15, and then add the 0 on top, and that's 16. This is why we multiply by 16 here. Now, each number is positioned by its power. So this is to the power of 3, again, because we begin counting from 0. You have to remember, and you have to understand that computers count from 0, not from 1. 0 is very important in computer. So here, this is to the power of 3. So multiply by 16 to the power of 3. And if it's actually easier for you, you can start from the right even. So F, we know it's 15. So F is 15 multiplied by 16 to the power of 0. D is 13. So 13 multiplied by 16 to the power of 1. B, we know it is 11. So 11 multiplied by 16 to the power of 2, and then 9 multiplied by 16 to the power of 3. If it's easier for you, you can do it from the right to left. So then you can start from 0, 1, 2, and 3, and then you multiply all by 16 because hexadecimal is base 16, or the maximum you can reach in hexadecimal is 16 digits. Okay? So yeah. Optional octal numbers. The octal system refers to base 8. In other words, it uses the digits between 0 and 7, while the hexadecimal system uses base 16 and groups 4 bits. The octal system uses base 8 and groups 3 bits. The table below shows how the octal digits relate to their binary counterparts. Now, again, they are all the same. Since this is base 8, you then multiply by 8 and then add to the power of whatever range is in there. Okay? What is the hexadecimal FF in binary? Okay. Now, if you want to get FF in binary, this is like the biggest number. So these are going to be all ones. I don't even have to think about it. Because F is the highest hexadecimal. It is the 15. And we know that in binary, four ones or 4 bits of ones is 15. It is the highest number that you can get. What is the hexadecimal AB in decimal? Okay, so you want to convert from hexadecimal to decimal. Now we know that hexadecimal is 16. So what we could do here, starting from b, we know b is 11. So 11 multiplied by 16 to the power of 0. And then 10 multiplied by 16 to the power of 1. Okay, so 11, this thing is 11. And this thing is going to be 160. So this will be 171. Okay, so this is, decimal is like our normal numbering system that we use, which is base 10. Convert the hexadecimal FFF to decimal. After you round up the decimal value to the nearest million, how many millions is that? All right. So we want to convert this to decimal. This is going to be a bit interesting. So let's remove all of this and let's do it ourselves just to make sure that we understand things correctly. We have FF, FF, and FF. Okay, we don't care about these. So we can like split them all into their own thing. Now we know we're starting from the right from 0. So 0, 1, 2, 3, 4, and 5. Okay, so F is 15. So 15 multiplied by 16 to the power of 1 or 0, 1, 2, 3, 4, 5. And then we have 15 multiplied by 16 to the power of 4. 3, 2, 1, 0. This is going to be a humongous number. Okay. Let's do it one by one. Now, if only I could use the calculator to 15 to the power of Windows calculator to the power. Scientific. Oh, EXP, is that the exponent or do I need to do this? Type the exponent and press equal. So 2 to the power of 3, is that? Oh, XY. So let's say, for example, 1 to the power of 2 is 1. Okay, so 2 to the power of 3, 8. Okay, there we go. Thank you, Google. All right, let's cancel this and let's go back to our notepad real quick. Okay, so 15 multiplied or times 16 to the power of 5. Holy moly. All right. Next, 15 multiplied by 16 to the power of 4. If I can copy that, that would be great. Thank you. Let's remove the things here because we're gonna just copy them and paste them in to just calculate all of them. So 15 multiplied by 16 to the power of 3. By the way, I don't have to click. I could just write it Shift 6 on my keyboard. All right. 15 multiplied by 16 to the power of 2. All right. And then 15 multiplied by 16. I don't even need to add to the power because everything to the power of 1 is itself. So 15 by 16. And then this is going to equal 15. Because I know that this is going to equal to 1. So I can show you. 16 to the power of 0 is going to equal to 1. So 15 multiplied by 1 is 15. So let's add these plus this plus this plus this plus this plus this equals, and there we go. This is the full number. Now, how many millions? It's 16 millions. Okay, let's round up. I think they said after you round up the decimal, so that will be 17 million. Because when you round up, you just increase 1 there. And we got it correct. Let's actually make sure that our answer is correct. which should give me the exact same thing. There we go. 16,777,215. Cool. So the conclusion, we are going to conclude that in this room, we covered several topics related to how numeric values are represented and stored in computer memory. We covered the following systems: decimal, binary, hexadecimal, and octal. Moreover, we learned how a color can be represented. We cover bit, byte, and hex color. Data encoding room, we will explore how the alphabets of the various languages are saved. In addition to letters, we will see how emojis are saved as bits. This was also new for me, actually. I learned alongside you how the numbering system works and how hexadecimal and binary work in computers. I actually did not know how hexadecimal is base 16. I just learned that with you, and I learned the values of the numbers here, which is great, which is super duper great. Okay. Octal also, I don't think we did any sample on octal, but it is like pretty simple. It is the exact same thing as a binary, but you multiply by 3. You multiply by 8, and you just have 3 bits together. Okay. So yeah, this is it. Thank you for watching. In the next video, we are going to be going over data encoding. So again, I'll be posting these in a playlist called Software Basics. So the name here. So make sure you follow in sequence, and give me a like, give me a subscribe, give me comments encouraging me that what I'm doing is good and it's actually helpful for you. All I'm trying to do is give back to the community that I learned from myself. My 8 years of experience of web development and cybersecurity right here is coming from the community. I did not go to college for this stuff. All I learned from was YouTube. Also add to that my English. So I even learned English just from the community, and English is not my main language, of course. It's not my mother tongue. So I learned that also from the community. So the community is great, and all I'm trying to do is give back to the community. If you think these videos are helpful, give me a like, give me a subscribe, give me comments letting me know what I'm doing good, what I'm doing bad. Any constructive criticism is always, always welcome. Well, without further blabbing, thank you for watching. If you've reached this part, I'll see you in the next one in data encoding. See you.